Hey guys, and welcome back to another video on the channel. In today's video we're going to be pretty much going over a brief introduction to Hawking radiation and how to measure the temperature of a black hole. So this formula was made by Stephen Hawking. It pretty much measures the temperature of a black hole from a particle from the event horizon. So let's just get straight into it and see how he worked out this formula here. Okay, so to start off with, we're going to use the principle of thermodynamics. So the rate of change of energy is equal to the sum of the rate of change of heat plus the rate of change of work. Now, for this derivation, we're going to assume it's an isolated black hole in space. So there is no work done on it, so that term is zero. So dW will be zero. So in other words, dE is going to be equal to dQ. Okay. Now we're going to pretty much put in our equation for entropy. So the rate of change of entropy is equal to the rate of change of temperature divided by the absolute temperature in Kelvin. Okay. We're going to rearrange this to make dq the subject. So in other words, multiply both sides by capital T to get this following expression. And now we're going to substitute this into the expression above. So we'll get dE equals ds times T. Okay? And from this, we're going to divide both sides by ds. So we get the temperature is equal to the rate of change of energy divided by the rate of change of entropy. Now all we're going to do is a little mathematical trick and rewrite the right hand side. So we're going to have the rate of change of entropy divided by the rate of change of energy to the power of -1. Now the reason we've done this is because we're going to make a substitution later. Now, we all know Einstein's famous equation that E equals mc squared. But if we were to differentiate both sides, we get the rate of change of energy is equal to the rate of change of mass times the speed of light squared. The speed of light is a constant, so that won't really change. So in other words, we get an expression for dE. Now we're going to put this into our equation above to get this following expression. Now, the speed of light is a constant, so we can actually take that out. Now, when we take it out, we'll have the speed of light squared to the power of -1. So it'll just be the speed of light squared outside the expression like this. Okay. So now that we've got this following expression, we're going to need some other stuff. So pretty much the entropy of a black hole is equal to Stefan Boltzmann's constant times the speed of light cubed divided by 4 h bar times gravitational constant times the area of a black hole. Now h bar is just Planck's constant divided by 2 pi. And we're also going to need the equation for the area of a black hole. So the area of a black hole is equal to 16 pi times Newton's gravitational constant squared times the mass all squared divided by the speed of light to the power of 4. All we're going to do is substitute our area into our entropy equation. So if we do that, we'll get this following expression, and we can see the speed of light is going to cancel out a couple of times, and we can also simplify that 16 to power of 4. So we get this following expression, that the entropy of a black hole is 4 pi times Stefan Boltzmann's constant times Newton's gravitational constant times the mass all squared divided by h bar times c. Okay. So with this, we're going to differentiate both sides with respect to the mass. So we'll get the rate of change of entropy with respect to mass. Bring that power down the front, so we'll get 8 pi, and that m gets reduced to a power of 1 rather than a squared. Okay. Now from this, we can actually substitute this into our equation here to get this following expression. Now all we're going to do is rearrange it by flipping it upside down because that's -1, and we get this following expression. And that is the temperature of a black hole. So all we need pretty much is the mass pretty much, because if you notice, if we look at this equation here, so if I get all of this here is just constants. So temperature is proportional to the inverse of the mass of a black hole. So pretty much the heavier the black hole, the temperature is going to be really affected by its mass purely. Okay. Now let's try and understand what's actually happening. So all we've got to imagine is pretty much this idea about virtual particles. So on the event horizon, virtual particles pop in and out of existence. So for example, what is actually happening? So virtual particles can pop in and out of existence. For example, an electron and a positron can annihilate each other to form electromagnetic radiation and then reappear to form this energy. So this can be represented by this Feynman diagram. So we have an electron and a positron going towards each other. They form a photon and then reappear out of nothing. So what's actually happening is, imagine this is a black hole, and we've got particles popping in and out of existence on the event horizon. Now, at some point, one of our particles is going to go straight this way, and one is going to go straight into the black hole. That means one of them will escape the black hole, and common particles are photons. So we can measure the temperature of these things. Now, if a particle is leaving the black hole, it's taking away mass. That means slowly over time, the black hole is losing mass. That means it's evaporating. And this is the idea of Hawking radiation, that when particles pop in and out of existence, there's a probability that half will go out into the universe and half will go back into the black hole. However, at the moment, it's not really taking effect, and you'll see why in a second. So when virtual particles appear on the event horizon of a black hole, half of them go into the black hole while half go into the universe, thus taking away mass from the black hole. Hence, over time, the black holes will evaporate. Common virtual particles like photons can escape the event horizon and be measured, and the temperature of the event horizon can be measured. And we just proved this formula for the temperature of a black hole, where h bar is Planck's constant divided by 2 pi. K is Stefan-Boltzmann's constant. G is Newton's gravitational constant. Pi is pi. Mass is in kilograms, and T is for temperature in Kelvin. Okay. Now, what's happening right now? So, since the temperature of black holes are lower than the cosmic background radiation, all existing black holes have an overall gain of mass. So, pretty much they're absorbing energy from the cosmic background radiation faster than they're evaporating. And this will continue pretty much until the temperature of black holes, until the temperature of the universe goes below the temperature of black holes. So if you were to calculate the temperature of a black hole with the mass of Earth, so the mass of the Earth is 5.97 times 10 to the 24 kilos. That is terrible writing. Let's rub that out. Eraser. If it loads. Oh, it's not working. There we go. So, if we were to calculate the temperature of a black hole for just, let's say, the mass of the black hole as the same mass of the Earth. So the mass of the Earth is 5.97 times 10 to the 24 kilograms. Okay. Now we know the temperature of a black hole is h bar multiplied by the speed of light cubed divided by 8 pi times Newton's gravitational constant times Stefan-Boltzmann's constant times the mass of the black hole. Okay. Now we're going to say it's the Earth. So if we were to put this in our calculator, this is what we're going to have to put. Planck's constant up here, so 6.626 times 10 to the minus 34 divided by 2 pi, so that's h bar, times by the speed of light squared, so 3.0 times 10 to the 8 all cubed, divided by 8 pi times Newton's gravitational constant, which is 6.67 times 10 to the minus 11, multiplied by Stefan-Boltzmann's constant, which is 5.67 times 10 to the minus 8, times the mass of the Earth, which is 5.97 times 10 to the 24. Okay? And if you were to put that in your calculator, you get roughly 5.01 times 10 to the minus 18. So we can see it's quite cold relatively. So really heavy black holes are going to have a very low temperature roughly. So only small black holes with low masses are going to have a relatively hotter temperature. Until that's lower than roughly, until this temperature of the background radiation is lower than most black holes, they won't start evaporating just yet. But yeah, that's about it. That's an introduction to Hawking radiation, a brief overview. I hope you enjoyed this video, and like and subscribe.